Alright, so right now I want to talk about what happens when you throw something. Okay, so let's say we throw something, it's flying along, gravity's going to pull it down, right? But this is really different from anything we've done so far because in this case where we've thrown something, it's moving this way and this way, right? I threw it this way, ends up going downward. So everything we've talked about so far was things moving in one dimension, so like up and down or side to side. Now this is a scenario where we have two dimensions of motion because something is moving side to side and up and down at the same time. And that really just kind of adds another layer of complication for us, okay? And because what happens is at any moment it's going to move in both directions, right, as it kind of falls downward. Okay? So the thing that's important for us to think about and will make this easiest to analyze is that we can look at things moving side to side and things moving up and down. So like in the case of something we throw, it's moving sideways and up and down at the same time, but we can actually look at those parts of it separately, okay? Because when we throw this object through the air, it experiences just one force, okay, that gravitational force that pulls it downward. And that's the only force it experiences, which means that the only acceleration it has is downward, okay? So let me show you what that means for us. So let's go ahead and work out a problem together. Let's say that if we have a cliff, we're throwing something off of it with a speed of, let's say, 15 meters per second, okay? And let's not worry about the height of the cliff right now. Let's just say it's a really, really tall cliff, and we're going to throw this object off the cliff. And we're going to kind of break up what's happening to this object over time. Let me actually add the starting time. Start with this. At time 0, we have this object that we're throwing horizontally, and let's say that it's experiencing a downward gravitational force. Okay, there's no horizontal force it's experiencing, which means that our horizontal acceleration, since nothing's pushing it sideways, this is 0. Okay, we have a horizontal velocity of 15 meters per second. We have a horizontal displacement of 0 meters because it hasn't moved sideways at all. Because we have a downward force, we have a downward acceleration of negative 9.8 meters per second squared. And we have an initial downward velocity, since when we threw it, it's only going horizontally, we have an initial downward velocity of 0 meters per second. Since no time has passed, our final velocity is 0. And since no time has passed, our displacement is 0. Okay, so as we continue, we know that our initial velocity for the whole time here would be 0. We know that our y acceleration the whole time is 0. And because our free body diagram only has a downward force, our horizontal acceleration would be 0. So I'm going to go ahead and fill those in real quick. So I've gone ahead and filled in these 4 rows here. Okay, and as we continue, I want to mention one other thing, our horizontal velocity. If our acceleration is 0, what is that going to say about our velocity horizontally? What it's going to say is that our horizontal velocity will remain constant. Okay, and this is something really important to understand about projectiles. Alright, we can assume that their velocity side to side horizontally is constant, and this is true for all projectiles. Now, in reality, it's not perfectly constant because it's slowed by air resistance, but they will continue to move horizontally at relatively the same speed without anything affecting them, which means that after 1 second, it's traveled 15 meters horizontally, and then 30, 45, 60, and so on. Okay? And so like after 7 seconds, since it's moving at a constant velocity, we can just use this equation so that delta x is equal to v times t. Okay, well that means that 15 meters per second for 7 seconds, well that's going to give us let's see, 70 plus 35, so 105 meters. Okay? You can fill out the rest of that row on your own. Okay? So now let's get to these last two rows. Okay? Well, since it's accelerating at negative 9.8 meters per second squared, we have to use kinematics here. So at 1 second, to find our velocity, we would use this equation right here. So v equals v naught plus negative 9.8 meters per second squared times 1 second. This is equal to 0. So v is equal to negative 9.8 meters per second. Okay. And if we continue at 2 seconds, it's going to be twice that because we put the 2 right there. That's going to be negative 19.6 meters per second. Okay, and so on. Alright, we can find our displacement, delta y equals v naught t plus 1/2 at squared. This is equal to 0. So delta y equals 1/2 times negative 9.8 times 1 second squared. Okay, that will be negative 4.9 meters after 1 second. Okay, now I'm going to let you go ahead and fill out the rest of this table. Okay, so now we're going to try to actually do some problem solving with a horizontal projectile. So let's say that we're standing on top of a 100-meter cliff and we throw something horizontally with a velocity of 25 meters per second. And let's say we want to find how far away from the cliff it's going to land. Okay? Well, the way that I like to analyze these problems, it's helpful if you say really organize, and we organize x and y. Okay, since we know that things move at a constant speed horizontally, then the only equation we use on the x side is this. And we're only comparing these three variables. Okay, we don't know its displacement. We know that the velocity here is 25 meters per second, because that's how fast we threw it. We're throwing it horizontally, so all in the x direction. And then time is a scalar. It doesn't have direction. It isn't just for the x direction or the y direction. It happens separately, so I'll put it down here. Okay, and then we don't really know how long it's going to take to hit the ground, so we don't have value for time. Then in the y direction, we know a couple things too. We know, for example, that the initial velocity is equal to 0. Okay, we know that acceleration is negative, well, it's 9.8 meters per second squared. We'll say that for this one, and it's up to you to choose this, we'll say for this one that up is positive, which means that acceleration would be negative. Okay? And then we also know that the ground is 100 meters below where we're throwing this from, so we're going to have a displacement of negative 100 meters. Okay, so we have these three variables. The other thing we can know about it is its final velocity, but we don't need that here. Since we want to know how far away it is, okay, that's what we're looking for this. We're looking at this equation to find x. We need to know time and velocity. We have velocity, we don't know time. Okay? Well, in order to find time, we're going to have to look over here with these y variables. Since it's falling and being pulled downward by gravity, we can actually find how much time it would take to hit the ground using this equation. So we're going to go ahead and plug into here. Okay, initial velocity is 0, so we can get rid of this. And we'll say negative 100 meters equals 1/2 times negative 9.8 meters per second squared times t squared. Okay, that gives us negative 100 meters equals negative 4.9 meters per second squared times t squared. We'll divide this over and take the square root. Okay, so we divide this over and we get 20.4 seconds squared equals t squared. We take the square root of both sides and get a time of 4.5 seconds. Okay, and so that's how long it takes to hit the ground. Okay, well now, if we want to find displacement, I have the piece for time and for velocity, so we can solve for displacement. So 25 meters per second equals however far it's going to go horizontally divided by 4.5 seconds. So I'll multiply that up to the side, and I'll find out that it's going to travel a distance of 113 meters by the time it hits the ground. Okay, so if we can imagine this is its path. Every second that it's in the air, it's going 25 meters. Okay, until it finally hits the ground. So since it was in the air 4.5 seconds, it went 25 meters every one of those seconds. Okay, and then it went half of 25 meters in that half second. Okay, and so this is an example of a problem with a horizontal projectile.